Hi everyone, this is the first video for section 6.1. So we're starting off talking about fractions, and this section covers a lot of material. But the first thing it covers is just kind of the basic definitions of fractions, just reminding you what a fraction is and kind of the vocabulary that we use to talk about it. So if a fraction is defined as a number of the form a over b, where b is not equal to 0. So we call a the numerator, and we call b the denominator. And the only conditions, like I said, on a and b are that b is non-zero. So fractions can look like anything. They can look like a whole number over a whole number, an irrational number. They can have decimals, they can have negatives, they can have variables like x. So all of these things are valid fractions. So at this point, I want to point out the difference between the fractions and the rational numbers. So remember that the rational numbers are defined using the step builder notation as a over b, such that b is non-zero and a and b are integers. So the rational numbers are the fractions that are just made up of the integers. So in this list, only this one is a rational number. So a lot of times people tend to use the phrase rational number and fraction interchangeably, especially when we start talking about ratios. But just remember here that based off how we define rational numbers and how rational numbers are defined in mathematics, that rational numbers are fractions that specifically deal with integers. Another thing to note is that a fraction is just one number, which can be difficult for students to understand because, for example, if we're looking at the fraction 3.4 over -7, this is one number, even though it may seem like we use two different numbers to denote it, right? 3.4 and -7. This is just one number. And so this is kind of why fractions are treated a little bit different, because they seem like they would be two numbers, and we want them kind of intuitively. We like to have things be familiar, and we like to have things work the way we've seen it work before. So it would be really nice if we could treat this as two numbers just with a line between them, but because we're treating this as one value, this makes fractions work a little bit differently. Okay, so now we can model fractions in a lot of different ways. So really, I just kind of listed them here. So we have length models, which are number lines, these rods, fraction bars, fraction strips, line segments as well. We also have set models. And so the set models can be discrete circles, counters, tiles, etc. But one thing that people often use as set models are coins, are really commonly used as set models. And then area models can be really, rectangles, circles, geoboards, pattern blocks, anything just kind of physical and geometric kind of go on our area model. And so all of these are covered in a lot more detail with more examples in the book. But I didn't think I could say anything better than kind of what's in the book. So this is covered on pages 198 and 199. So go back to your book and read and make sure you understand the different area models that you can use. There's really, truly a lot of them, but just make sure you're kind of familiar with them and that everyone makes sense to you. So one thing we are going to talk about is looking at this example, which this is an area model. So this is an area model because one way you can think of really an area model is that it's something geometric. Something geometric is usually always going to be an area model. And so we want to determine what fraction of this octagon is shaded. So one way we can do this is to kind of break things up into smaller shapes to count them. Just like with some of the area models they talk about in the textbook, you take the figure that you're given, so like a circle, and you break it up into however many equal parts, and then look at the shaded parts of that. And similarly, when you do that with rectangles or squares or anything like that. But here we just are going to do it with an octagon. So we want to break this up. And so it's already kind of nicely on this grid that we can draw. So if we draw this on this grid, we can break it up into these squares and these triangles. So if you are confident enough, you can just keep it in these squares and triangles. However, what I would do if you're not as confident in this is to make sure that you just break it up into things that are all the same shape. So you break up everything into triangles. That way, it's just easier that you're counting objects that are all the same. Okay, so now we have this object with these triangles, and we just want to count how many triangles there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and 28. Okay, so there are 28 triangles here. So well, let's go ahead and do this. So if we want to determine what fraction, we need to have a numerator and a denominator. So the denominator is the total amount of rectangles. And the numerator is just going to be how many of the different rectangles are shaded. So we can see that 1, 2, 3, 4, 5, 6, 7, 8 of the different triangles are shaded. So then once we have our numerator and denominator, we can make our fraction. So our fraction is 8 over 28. So 8 28ths of this figure is shaded. So if you decided to do this where you didn't break everything up into triangles, where you still had some squares and some triangles, you may get an answer that looks different, that is equivalent. And we may just be so used to simplifying fractions that we would automatically just say, yeah, this is 4 over 14. But we'll talk more about equivalent fractions in one of the later videos to just kind of formally know what that means. But the last thing I want to note right now is that we usually think of fractions as a part to whole. And that's kind of exactly what we did in this example. We looked at all of the triangles in the shape, and we just identified which part of them were shaded. But fractions can also be used to represent part-to-part relationships. And that's going to come in when we talk about ratios in section 6.4. So just to note that although we typically always think of fractions as being, right, a part over a whole, that's not the only way that we can think about them. Okay, so since that's the end of that page, that's all for this video.